Continuation of the previous lecture of some theorem on tree. In the last lecture we discussed two different theorem. Now we start the third theorem of related to tree. It says that any connected graph with n number of vertices and n minus 1 number of edges is a tree. In the previous theorem we say if a graph is a tree with n number of vertices, there must have exactly n minus 1 number of edge. In this theorem, do not mix up these two theorem. It says that any connected graph with n number of vertices and n minus 1 number of edges is a tree. যদি কোনো গ্রাফে n খানা ভার্টেক্স থাকে, n minus 1 খানা এজ থাকে, তাহলে সে ট্রি হতে বাধ্য। ঠিক আছে, তাহলে একটা গ্রাফ, if a graph has n number of vertices and n minus 1 number of edges, if you want to prove that this graph is a tree, in that case you have to prove that this graph has any cycle or this graph should be a connected graph. If you can prove that this graph is a connected graph, has no cycle, therefore you can easily say that this graph should be a tree. So the motto is clear for us. Let G be a connected graph with n number of vertices. G be a connected graph with n number of vertices. First we consider G be a connected graph with n number of vertices and n minus 1 number of edges. Let it be possible G is not a tree. Here we assume that, suppose we consider this graph is not a tree. Since the graph is a connected graph and still the graph has no the graph is not a tree, in that case the graph must have a cycle. Am I right or wrong? The graph must have a cycle, otherwise the graph should be a tree, na? So then G contains a cycle. So here we mention G contained a cycle. If G contained a cycle, let A be an edge of this circuit. We just consider E be an edge of this circuit. সেই সার্কিটের একটা edge consider করলাম. Then the subgraph should be n minus 1 number of edges. Yes or no? Then the subgraph must have n minus 1 number of edges. If we delete this edge, then the subgraph exactly n minus of e number of edges. Deleting the edge, the subgraph obtained from G by deleting this edge is still a connected graph. Still it's a connected graph, na? G minus E has n minus 2 number of edges. Then G minus E graph has n minus 2 number of edges and n is the vertices. This is not possible since we know that a connected graph with n number of vertices has at least n minus 1 number of edges. That is the theorem of connected graph. If a graph is a connected graph with n number of vertices, then this graph must have at least n minus 1 number of edges. But still we can find a graph G minus E, which is a subgraph of the graph G, has n minus 2 number of edges while the number of vertices is n. Still it's a connected graph. It should not be possible. So our assumption is bull. What is our assumption? Our assumption is exactly this. So our assumption is no, G is not a tree. So G should be tree. Yes, clear? So move to the next case. Definition of minimally connected graph. What is the meaning of minimally connected graph? A connected graph G is said to be a minimally connected graph if remove of any edge without removing the n vertices. That means deletion of the edge from G disconnected. কোনো একটা গ্রাফকে মিনিমালি কানেক্টেড মানে সবচেয়ে কম এজ দিয়ে কানেক্টেড আছে, কখন বলবো? যদি কোনো একটা এজকে আমি ডিলিট করে দিই, গ্রাফটা ডিসকানেক্টেড গ্রাফ হয়ে যায়। If we delete a edge from the graph, it becomes a disconnected graph. Then we say that the graph is a minimally connected graph. Here is the figure. If we delete any edge of this graph, it's become a disconnected graph. But according to this graph, if we delete E2, then this graph still it's a connected graph. Therefore, this graph is not a minimally connected graph. A graph is a tree if and only if it is minimally connected. The same next theorem. একটা গ্রাফকে আমরা ট্রি বলবো যদি গ্রাফটা মিনিমালি কানেক্টেড হয়। A graph is a tree, again we repeat, a graph is a tree if and only if it is minimally connected. Necessary condition. Suppose a graph G is a tree with n vertices, therefore it has n minus 1 number of edges because it's a minimally connected. Therefore its number of edges should be n minus 1 edges. If one of the edges is removed from G, then it has n minus 2 edge and G becomes disconnected graph. Okay, আমরা ধরলাম G একটা ট্রি যেখানে n খানা ভার্টেক্স আছে, n minus 1 খানা edge থাকবে। According to the theorem of tree, n minus 1 number of edges should consist. If one of the edges is removed from G, then it has n minus 2 number of edges. G becomes a disconnected graph, so G is a minimally connected. Okay, so the tree is the graph which is known as the minimally connected graph. Sufficient condition. Suppose G is a minimally connected graph, still it's not a tree. Okay, then you have to prove that it's a tree. Therefore the number of edges of G is greater than n minus of 1 because the graph G consists exactly n number of vertices. If the graph is a minimally connected graph, then the number of edges should be n minus 1. If we consider the graph is not the minimally connected graph, then the number of edges should be n minus 2. As G is connected, if possible, G has a circuit, and it is also connected. If one edge of this circuit is deleted, যদি কোনো একটা এজকে আমি সার্কিট ডিলিট করে দিই তাহলে গ্রাফটা স্টিল কানেক্টেড থেকে যাবে। ফ্রম জি ইট ইজ এ কন্ট্রাডিকশন সিন্স জি ইজ এ মিনিমালি কানেক্টেড। আমি ধরেছিলাম জি হচ্ছে মিনিমালি কানেক্টেড যেখানে নাম্বার অফ এজেস হওয়া উচিত n minus 1, তার মানে কোনো একটা এজকে যদি বাদ দিয়ে দিই তাহলে সেটা ডিসকানেক্টেড হয়ে যাবে। কিন্তু স্টিল উই কনসিডার ইটস নট a tree. If it's not a tree, that means it must have a cycle because it's a connected graph. If it has a cycle, that means if we delete a edge from this cycle, still the graph becomes a connected graph. Since it's a connected graph with n minus 2 number of edges, which is impossible, which contradict that the graph G is minimally connected, সবচেয়ে কম ভাবে connected, it is never possible, so the graph should be a tree. It's a very important theorem for multiple choice question also. The number of vertices in a binary tree is always odd. কোনো একটা বাইনারি ট্রিতে নাম্বার অফ ভার্টিসেস অড সংখ্যা, মানে 1টা 3টে 5টা 7টা 9টা 11টা 13টা 11 13 19 15 and so on. A binary tree should not consist any even number of vertices. That's very important theorem. Okay, the number of vertices is always odd. What is the definition of binary tree? A tree is said to be a binary tree if there is a vertex of degree 2, all the remaining vertex is degree either 1 or 3. So let A binary tree has n vertices. আমি ধরে নিলাম একটা binary tree তে n খানা vertex আছে. You have to prove that this n should be a odd number. আমাকে প্রমাণ করতে হবে এই n টা হবে odd number. Since binary tree has one vertices of degree 2, since it's a binary tree, it's one vertices of degree 2 and the remaining vertices are of degree 1 or 3. তার মানে বাকি ভার্টেক্স গুলো ডিগ্রি 1 কিংবা 3 হওয়া উচিত, 1 or 3. So there are n minus 1 number of vertices of odd degree is a binary tree. The remaining n minus 1 vertices should be a odd degree vertices. Which vertices is called odd degree vertices? Those vertices are called the odd degree vertices if their degree is an odd number. Since it's a binary tree, one vertices of degree 2 and the remaining vertex is degree either 1 or 3, that means the remaining vertices should be a odd vertices. That means n minus 1 vertices, n minus 1 number of vertices are of odd degree in the binary tree. we know that the number of vertices having odd degree in a graph is even. আমরা এটা পড়ে এসেছি থিওরেমে, যে কোনো গ্রাফের odd degree vertexes সংখ্যা always even হয়. Number of odd degree vertex is always even in any graph odd degree vertices is a number of odd degree vertex is always even. Since tree is also a graph, therefore the number of odd degree vertices should be even. So n minus 1 is an even integer. তাহলে n minus 1 একটা even integer হলো, hence n is an odd integer. How can I say? When we add 1 with a even number, the number should be odd number. যদি তুমি এক যোগ করো কোনো একটা ইভেন নাম্বারের সাথে, সেটা অড নাম্বার হতে বাধ্য। So when we add n minus 1 plus of 1, n minus 1 with 1, the result becomes n should be odd. So n should be odd integer. That is, the number of vertices in a binary tree is odd. Another very important theorem: the number of pending vertices in a binary tree is n plus 1 by 2. ধরো তোমাকে বললো যে একটা binary tree number of vertices is 13, then how many number of pending vertices are there? কি করবে? তুমি কি ছবি আঁকবে? No. You can easily use this theorem. 13 plus 1 by 2, that is 7 number of pending vertex. What is the definition of pending vertex? A vertex is said to be a pending vertex if its degree is 1. So let x be the number of pending vertex in a binary tree. আমি ধরলাম x খানা pending vertex আছে কোনো একটা ট্রিতে, ঠিক আছে? That is, x is the number of vertices of degree 1, সেই সমস্ত vertex যার degree 1. Now t has only one vertex of degree 2, it's the root vertex. Binary tree একটা vertex যার degree 2 থাকবে, and each of the remaining vertex is of degree 3. That means the remaining vertex should be degree 3. So sum of the degree of all the vertices, if we summarize the degree sum, the first one, x number of pending vertex whose degree sum should be x, one vertex whose degree is 2, and the remaining vertex is degree 3. Therefore the degree sum should be 3 into, here the n represent the number of vertex. Why we subtract 1? Because one of the vertex whose degree is 2 already added, and x is the number of pending vertex. So the number of vertex whose degree is 3 is n minus x minus 1, n minus x minus 1. So after calculation the result becomes 3n minus 2x plus 1. We know that it is the basic theorem of graph theory, and second lemma says that the number or degree sum of any graph is equals to 2 into number of edges. Since the number of edges in a tree with n number of vertices should be n minus 1, যে কোনো ট্রিতে n খানা vertex থাকলে n minus 1 খানা edge হয়, therefore the degree sum should be 2 into n minus 1. According to our calculation, degree sum becomes 3n minus 2x minus 1. So 3n minus 2x minus 1, that is equals to 2n minus 1. After calculation, x become n plus 1 by 2. Hence it's the result, that is the number of pending vertex is n plus 1 by 2. In the next lecture we move to another sum theorem of tree. Happy learning. Thank you for listening.